All right, so we continue with the talk by Robert Smiech from Edinburgh, who's going to tell us about G-birational. Robert?
Okay, so thank you for giving me this opportunity to speak. I know that my handwriting is terrible, so that's worse, and then you can screen up. Okay, let's go.
So it is calligraphic in comparison with what is going to form.
Okay, so first part is like G, M, and P notions and questions. Okay, so there are like in this theory, like this is very classical stuff, and I will mention like results that are due to like, let's say, circle that is like centered around Pezzo. Jak jego Jasiński and some collaborators. Yeah, okay, so this is joint work in progress, so not everything is yet ready with Aurore Boitrel. Yeah, okay, so this GMNP, so everybody knows what MNP is, like we take varieties with some attractions, we get some modified space. So I mean, this part that I am more interested in this Kawamata negative. So, okay, so we have like, we can add some group action to this, right? And study what happens when we have some group action. So there are like two settings that are called algebraic. When okay, so when the field is, let's say, algebraic closed of characteristic 0, and the group that we study is some finite group, the group of automorphisms of variety. And people study those things because they are useful in particular to study the cremonal, to study the subgroup of cremonal. So this is like, no, there is also this arithmetic setting. Where K is not algebraically closed, and when we study some, let's say, Galois group. And of course, we can mix them, right? I can study some group and I mean some subgroup of automorphisms, some Galois action. So definition, fundamental definition is that G Mori fiber space and sometimes people use this quite MFS, quite very badly, but not. Is a projective morphism pi x y where dimension of x is bigger of dimension of y. So there are some non-trivial fibers of G varieties such that x is terminal all G invariant while divisors are Q Cartier. So this is like, you know, in the usual MMP, we study Q factorial varieties because we want to intersect stuff. So this is like the minimal version of this assumption is G set that I care about. G invariant while divisors are Q Cartier. A rank of Picard group of G invariant Picard group minus rank of G invariant Picard group of Y is 1. So this is like element G. So this is like elementary Mori contractions, and minus kx is pi amp. So this is like a Mori fiber type Mori contraction. Yes, and if y is a point, if this contraction is a point, then x is G fan. So G fan is something that is second canonical contraction. Okay, and another important definition is that G fan is G solid if it is not G birational to a G Mori fiber space with positive dimensional base. Yes, so if I find something that is G-birational and it has a non-trivial contraction, not a problem, then it's not G-solid. G-solid, G-birationally rigid. If every G-birational map we have but yes, so rigid means that if I have a birational map, then in fact this this other variety can only be isomorphic to X. This doesn't have to be an isomorphism, but yeah. There is also this super rigidity, but we won't use this, so maybe I will skip.
So, I mean, this just means that solid means that the only Mori ray is that G Mori ray is the variety itself.
Okay, yeah, so I should mention that in dimension 3, so the study of these Gfanos was, I think, initiated by Prokhorov. There is like a series of 2 papers. And okay, so I promised also some questions. So, yeah. There is one more. Right. Okay, so this is like because it essentially came from this arithmetic.
That counts. In dimension, you make different Pezzo's with group actions. That's already the one is paper. IHS in the 60s.
Yeah. So in dimension 3, Prokhorov, yes. Product of the Russian school in general. Yeah, so Kolar asked the question is arithmetic set. But if I have a X that is a Fano over K, which is not algebraically closed, such that X is birationally rigid over the algebraic closure is X birationally rigid over K, over this field that we studied. So this is the non-trivial question and nobody knows. And the thing is that nobody believes that this is true, but nobody has a counterexample. So
what was the question?
This is the Kolar question. So I have a Fano over some field K. And I know that over the algebraic closure, it is birationally rigid. Is it birationally rigid over this field that I started, this smaller field? Okay, and so this is like posed by Kolar in this arithmetic setting, but there is like a variant that was is attributed to Chertsov Kolar, let's say. So this is like Vanya's modification of this original question. But I have H, the subgroup of G, and I have X that is H birationally rigid G Fano. Is X G birational. Yes, and as before, nobody believes that this is the case, but nobody can prove it. People are looking for.
So you're saying that the opposite usually gives something is rational over K bar, then it might not be K, but it's already non-rational. Will it be that I see it's not rational?
Yes, so in dimension 2, there is a positive answer to this question. By Jasiński. But yeah, we have dimension 3. We have a lot of stuff in dimension 3. We can like work on a lot of examples and try to analyze them. So yeah, in this work in progress, like we take one particular family of threefolds with a group action, and we started to study. Yeah, so I need to describe like what is the object of our study. So Fano family 114. Yes, so this is X is the Pezzo threefold of degree 4. I.e. This is a Fano with a row of X equal to 1. Picard group of X is generated by some line bundle L, where I mean
otherwise it's fine. This is exception of the quadratic G4.
yes, and if this is smooth, then yeah, okay, you are totally right, because it can happen. I mean, if this is yeah, so this is like a smooth one. Okay, so let me add. Yes, I do that. If this is smooth, then the picker rank is 1. Then if I can pick intersection of the quadrics that is singular, then no, not necessary. And there is also an interesting example when for one non-smooth case that is interesting. Threefold of degree 4.
Actually, I don't know.
So I'm going into it. Yes, so I have a smooth Fano threefold with picker rank 1. So the picker group is generated by a line bundle where L is like the half of the anti-canonical. Okay, and this L gives the embedding. gives the embedding into P5. And okay, L to the third is 4. This is this degree. Okay, and so there is a theorem of Takao. But every
Sounds to P gives an embedding where?
in P5.
P5. Okay.
Sorry, I said that my handwriting is horrible. Every such threefold is an intersection of two quadrics in P5. And moreover, so this is maybe not, but one of them can be picked to be smooth. Okay, great. So yeah, this is like, just an honest Fano family that is interested from the point of view of Fanos by themselves. So we need to think about the groups. So the automorphism. Okay, so
Or the complex number is equal between gymnastic, right?
no,
The intersection of the quadrics. Right?
no, because this has been parent two.
Yeah, but then you so this average of the curve and it's Weissman quadrant can to three curves and then you pull down the quadrant.
Okay. Yeah. Okay, yeah. Okay, so okay, maybe I yeah, so I have two quadrants. Yes, I have two quadrants, Q1, Q2. So in general, instead of studying two quadrants, I can study, like a pencil of quadrants that is sometimes. I can study a pencil of quadrics, and I can study like the determinant of this lambda Q1 plus mu Q2. And this has some roots, right? This is a polynomial in this complex number. Roots that are uniquely determined by P. Right, okay, and so the fact is that the pencil of quadric is determined up to ISO by roots of those things and Segre symbol. So I want to introduce Segre symbol because I think it's important. This is just something that encodes the multiplicity of the root. Okay, and yeah, so space. Theorem. Automorphism. So this theorem, I don't know to whom I can attribute it. Like you can find it with Avilov's paper, but this is some classical stuff essentially. The automorphism group of X fits into short exact sequence. So the automorphism group is in the middle, and then I have like these two guys on the left and on the right, and this is a subgroup of automorphisms of P1 preserving roots of delta, and this acts on P5 by keeping each quadric invariant. Okay, and yes, so there is a proposition that can be found in Myers rigidity again, because he studied intersection of two quadrics, that says that X is non-singular. Here is non-singular. Delta has distinct roots, and Q1, Q2 are simultaneously diagonalizable. Okay, yeah, so this is like a sense that I can like, pick a bunch of points in P1 and this determines this intersection, and I can just write down that Q1 is sum of xy squared, Q2 is sum of lambda I xi squared, where lambda I are distinct. Lambda I is different from Nice. Okay, so we have this is everything classical. We have a nice description of our guide, some guides, because like there are many of them, of course, and now we can study the geometry. Then so this is like 3G. So this, of course, like the study of this particular example is has been already initiated, just not finished. So there is a guy named Avidov, and he said that essentially the theorem that I will state very informally is that the only interesting cases are as follows. A, X smooth such that this short exact sequence that is on the left is essentially like this, out X and K and 0, and we have 4 cases. K is equal to S4, to K is equal to D3. I'm using this notation where this has 6 elements, symmetries of triangle. K is equal to D6, symmetries of hexagon, and K is equal to C5. And
Interesting cases in what respect?
yeah, so I will, after I finish stating the theorem, then I will explain what I mean by this. I will sketch what Agilov did, so what does it mean that we are in interesting cases. Yeah, the cases where we have something to do in this setting. And there is also like a unique, so this is like a singular toric intersection. But so this guy was then studied by Vanya, I guess Kishimoto and some third author, but I don't remember. But there is like a paper, toric G Fanos, and they solved the question of G rigidity of this toric guy. So I will just write Chertsov et al. Because I don't remember. Okay, so now, yeah. And okay, in all cases besides this case, such a intersection of two quadrics is unique up to isomorphism. But in this case, when I have D3 symmetry of triangles on the right, I have like one parameter family of these guys. Yeah. So what I mean by interesting cases. Okay. So as we want X terminal, we can exclude a lot of intersection of the particular, let's say, some curve are singular along some along the curve or something like this. We exclude a lot of cases. Then the rest of the singular members besides this one toric guy can be shown to be G-birationally equivalent to a quadric before or a G on one. Yes, so they are certainly not G-birationally rigid or not G-solid. Because I have either some fixed point or a line, I can project around it, and I get like this morphism that I'm interested in. I mean, directional. Okay, so we are left with this unique toric case that was handled by Vanya and his collaborators, and we are left with the smooth ones. Okay, so for the smooth ones, yes. So I have this thing, yes. This acts on P5 by keeping each quadric independent invariant. So this is essentially C2 to fifth. I just swap the I will switch the sign on the coordinates. Right? X1 goes to minus X1, X2 goes to minus X2, blah, blah. Yes. And this thing on the right, this is subgroup of automorphism of P1 that preserves roots of delta. I know that I have 6 distinct roots. So I need a subgroup of P1, finite subgroup of P1 that preserves 6 folds. So for most of the points, so for most values of lambda that determine like this intersection, I don't have. There is no group that exists. But I can like pull up the list of finite subgroups of P1, and I can check that I have more than this, but I have essentially yes. Okay, so finite subgroups of fixing a set of 6 points. I have not many bases. I can have C2, C5, C2 cross C2, D3, D6, S4. Okay, and of course I have also the trio. So in all of, I mean, in this case, when I consider in C6, yes, because I have P5, so I have C6. I have like a subspace of dimension 4 that is preserved. So I project it along it. So I project onto P1. I have a del Pezzo fibration because yes, I sit in P5. So I have a 3-dimensional fixed subspace. I project along it, and I map onto P1. I have del Pezzo fibration. So we have a non-trivial vibration. Okay. Yes. So this is what I meant by only interesting cases, where I cannot like immediately say, okay, I project, I am not rigid, I am rigid. I have to start the rigidity. We have to start that. Yes. So also a bit of set more. So there is like a proposition. So yeah, he in particular like started to work on this case 4, when I have a cyclic group of order 5. So he said that if G is the maximal subgroup, then X is G rigid. And if G is C5 or C10, then X is not G solid. Okay, so he took like 2 ends of the spectrum, big and small. Yes, so for the small, he observed that has a fixed point, so I can like blow up and get the second contraction. This is not, I know that it's not solid. For this, so if I have big groups and I want to show that it is G rigid, then like there is this machinery that maybe I will manage to introduce, maybe not, of Netter-Hano-Iskowski inequalities, which essentially says that, okay, if I have some birational map, okay, I have no written birational map. I have some mobile linear system, I pull it back, and then the pair X with this linear system with some coefficient is not canonical. So it has some center of being not canonical. And of course, like I'm working in G set. So there is like some G fixed center, which, since I'm working with a threefold, is either a bunch of points or a bunch of curves. And then I have to only check, because like this inequality, Noether-Van-Oiskowski inequality, gives me like a bound on the product of degree and orbit. So in our case, in this case, like this bound is 15. So I need to check, for example, lines that have orbit of length up to 15, or conics that have orbit length up to 7, and so on and so on. And if I exclude everything, then I say, okay, this is not possible. This is not possible to have a map from something that is different from X. That's how it works, but yeah, this is a lot of work. Okay. Here. So essentially, okay, so that's the thing. If you have a big group and you want to show, okay, this should be like a G-rigid, I use this Noether-Van-Oiskowski. But if I have something small, then maybe I have like more luck trying to show that it is not rigid or it is not G-solid, because I can somehow, draw something up, contract something, because since group is small, then there are maybe more curves points that I can blow up. Yes. So okay, so what is left? This is where I've been offended. So what is left? So here I will say about some of our results that are in progress. Okay, so yeah, we can like again get rid of a lot of cases by just employing some representation theory. Yes, so I have all these nice groups, and I have this action on X. I can maybe lift it to the action on cone over. So I have some representation of some other group. Yes, maybe some other group that I note like this on C6. Yes, and as before, I mean, I used this argument before. If this representation splits as 4 plus 2, then I can get rid of this case because I know that it has a del Pezzo vibration. So essentially, the only cases, because I study groups, I need to also study their subgroups, because like this is the issue with this thing that I need to do everything. I need to like check group by group for all the subgroups. So if I have any other splitting than 3 plus 3 or irreducible. Yes, so this might be an irreducible representation. This is an interesting case. Or 3 plus 3, this is an interesting case. Any other case, if I have any other splitting, then I have a sub-representation of dimension 4. So I do not care about this anymore. Yes, so the first thing is that for k equal to C5, any other subgroup that is maximal, yes, so if G is not equal to C2 or C5 or the whole subgroup, then X is not G solid. So this you will exclude just by looking at the representation. Okay. Okay. And so like if you look at so now this guy, we forget about this. This guy is done. So we have these three guys, and if you look at those subgroups for which like this representation on C6 splits as 3 plus 3, then essentially I don't have that many groups. In particular, like in all three cases, like the minimal subgroup, it's always is denoted G in this small groups database. It's denoted by 12 3, and this is isomorphic to C2 to C3. And okay, so I forgot to mention, but so I will say it right now. So from Fano theory, I mean general theory of Fanos, complete intersection of two quadrics has 3 blowups that still make it Fano. So blowup where C is a line, a conic, and intersection of two hyperplanes, which is an elliptic curve, is still Fano. Okay, so first thing that I might want to study are the blowups of X in a line, a conic, or intersection of two hyperplanes. But the thing is that by the representation theory again, I don't have this and I don't have this, right? Because line is a line, right? Two-dimensional subspace. I excluded them like at the very beginning by the just now by representation theory. I also not necessarily have like a hyperplane that would have an orbit too. Easy to see that there are such hyperplanes. So I can find some conics, and in some cases, so this is what I wanted to say really, is that yeah, in case of this in all 3 cases, when the representation splits as 3 plus 3, the numeral subgroup is this, and I can find the fixed conic. So yeah, just to give you an example, so if I have X is equal to sum X squared to 0 and yes, at my how does my group act? My group acts that it changes the signs on 4 coordinates, and I have like 2 such changes, and I swap them. So as you can easily guess, I can like exchange x0 to x2 and x2 to x4, and the same like 1 to 3 and 3 to 5. Yes, then I take like the if I cut my X by these 3 hyperplanes, then this disappears and I get just some smooth conic. Yes, I can even, for some bigger groups, for some groups of order 24, I can still use this conic and get a, so I get a conic, I blow up at this G-invariant conic, and I get a vibration, a conic bundle. So they are not G-solid for those groups. Okay. Okay. Yes. So the last thing that I want to say is that, of course, like we quickly ran out of Fano blowups. And then I can start thinking, okay, I need to blow up something more complicated. So there is like two things. So one thing is I can sometimes I don't get a fixed conic anymore, but I get two conics, two distinct conics. So the naturally, okay, let's blow up two conics because, okay, if one conic gives me a conic bundle, yes, birational map to rational, or gives me some rational map to P2, then maybe like, two conics will give me a map to P2 cross P2. But this does not give a good thing that would be interesting. So the next thing is to study some blow-ups that would give me weak funnels. Yes, and this is something that one absolutely adores. There is this paper of Gutron and Marshall where they study a lot of existence of these weak funnels. And also, yeah, also Young, Peternel, Rolf, and Fukuoka. So, such that, I mean, let's say smooth threefold that the anticanonical is big and net.
But not them.
No down, yes. Yes, so for example, if I
Anticanonical.
Hmm?
Anticanonical. Anticanonical.
anticanonical, yes. Yeah, so for example, if you blow up complete intersection of two quadrants in a curve of genus 1 degree 6, then this will give you a weak funnel that has deltas of vibration. But it's not easy to find such a curve, in particular smooth. So it might happen that I have like a degeneration of this curve. Because, such curve of genus 1 degree 6 can degenerate to just 6 lines. Yes, so it's easier to find, but this is not yet studied. I mean, to understand what is happening in case of such singular blow-up, I mean, work to yes. So I think I will end up here because this is just a work in progress. So a lot of work is yet to be done. So thank you for your attention.